Hello all, welcome to the Microprocessor lab. Today we'll be doing the addition of two 16-bit numbers by taking user input using MASM 8086. For this purpose, I'll be using two registers BX and CX, where BH, BL, CH, CL refer to the higher and lower bytes of the registers respectively. For taking user input and for display purposes, I'll be using the DOS interrupt in the category int21h. Now, this helps the user to handle the hardware resources such as the keyboard, display, hard disk, etc. Routines to refer to each of these resources are written as interrupt service routines for 21h instruction. These are called the function calls, and the function call is decided based on a function value, which is usually stored in the register AH. Here the function code 01h stands for inputting a character from the keyboard and echoing it on the display. So that character will be stored in the register AL. Function code 09h sends a string of characters to the display, and the offset of the string will be stored in the register DX. Function code 02h refers to outputting a character in the currently active display, which will be stored in DL in its ASCII code form. The function code 4ch refers to final exit to the MS-DOS or the parent task, and the status of this termination will be stored in the register AL. When you observe here, we'll see that except storing the offset of string, all the other function codes use an 8-bit register. Due to the same reason, while performing addition, we'll be taking the register as bytes rather than 16-bit. That is, the lower digits of each number will be written to CL, BL, and the higher digit will be written to CH, BH separately. Next is an instruction AAA, which stands for ASCII adjust after addition, which is usually performed after the addition of two ASCII coded operands to give a byte of result in AL. After the execution of this instruction, the result in AL will be converted to unpacked decimal digits. We'll see an example for the same. Suppose the value in AL is 6, 7. I'll check for the lower 4 bits of the register AL and see if it's less than 9. If it's less than 9, I will replace the higher 4 bits of AL with 0 and increment the value of AH by 1. Please note that the value of AH should always be cleared before performing an ASCII adjust, since the result will give a reflection on the same register. After ASCII adjust, the result of AL will be 0, 7. Taking another case, if the value of AL is 6A, where A is greater than 9, what we'll do is, we'll add 6 with A, which gives us 16. This is its hexadecimal equivalent. The value, that is the final value of AX, will be the higher digit will be sent to AH, the lower digit will be sent to AL. Initially, AX was 006A. After ASCII adjust, it changed to 0100. Now, we'll start coding. So, when we begin a program, we should inform the assembler the names of the logical segments to be assumed for different segments used in the program using the assembler directive assume. So the format of assume is assume DS is the data segment register colon data comma CS colon code. So data segment will be called data and code segment will be code. Now I'll start writing the data segment. So when we begin a segment, we'll give the segment name followed by the label segment. So data segment. Here I have three variables. Three of them will be strings to indicate the entry of two numbers and its sum. I'm giving the first one the name MSG. I'm defining it as a byte, so define byte. Then I give the values 0AH and 0DH. 0AH stands for feed input and 0DH stands for carriage return. So after executing this in combination, the cursor moves to the beginning of the next line, comma, the string to be displayed. And at the end of the string, a dollar sign is added. Similarly, I'm defining another variable MSG2 in order to display the string for second number, and lastly MSG3 to display the string for sum. Now I'll mark the end of the data segment using data end S, which stands for end segment. Now I'll begin with the code segment. Again, I'll indicate its beginning using code segment. Then I'm giving it a label named start. This is optional. So I'll give the label as start colon. Now, before you start, you should initialize the data segment. So this cannot be done directly to the segment register as it is not allowed. So we will use a general purpose register like AX for this. So the instruction will be move AX comma data, move DS comma AX. Next, I'll be printing the message that is corresponding to the entry of the first number. For this, I'll use the instruction LEA. LEA or load effective address loads the effective address formed by destination operand into the specified source register. Since I'm printing a string, I'll use the function code 09H. Here we'll see that dx will be the source. So the instruction will be lea dx comma message, and I'll move the value 09H to the register AH and then call the instruction int 21H. After this, the string will be displayed. Then I am reading the digits one by one. For the first number, I'll be first reading the higher byte. For reading a value from the keyboard, I'll use the function code 01H of DOS. So it can be written as move AH comma 01H int 21H. After this, the character read will be stored in the register AL. Since it needs to be moved to BH, I'll write the instruction move BH comma AL. Similarly, I'll read the second digit. Now the value of AL will be copied to BL. So I've completed reading the first number, which has its higher digit in BH and lower digit in BL. Similarly, I'll read the second number. For this, the message is MSG2. So LEADX message 2, move AH comma 09H, instruction int 21H. I'm reading the first digit of the register CX. the value of AL will be copied to CH. Then the second digit of second number will be read to CL. So I've got BX and CX. Now it is mandatory that while adding, one of the operands should be present in AL. So I'm copying the value of BL to AL. As we previously discussed, when executing ASCII adjust after addition, we should always clear the value of AH before executing this instruction. So I've cleared the value using move AH, 00H. Now I'll perform addition over the lower digits of both the numbers, AL and CL. AL actually contains the value in BL. I'll add and the result will be in AL. If there is a carry, it will be stored to AH. After ASCII adjust, I'll add a value 3030H to AX. Now, why do I add such a value? When we enter a number, if for example it's 1, it will be stored as 31H. That is its ASCII representation. So if I enter the value 2, it will be stored as 32H. So when you see, the difference between the actual value and ASCII code is 30. After this ASCII adjust, the result should be in a format that is understandable by the user. So to convert it into that format, I'll be adding 30 to each byte. Since we'll have the result in AL and if there is any carry in AH, I need both of them in the understandable format. I'll be adding 3030H to AX because there are 2 bytes in AX. Okay. Now the result in AL will be copied to BL because I'll be using AL for the addition of the higher digit. Similarly, AH also needs to be stored to another register AL since I'll have to clear AH before the next ASCII adjust. I'm clearing AH. Now what we did is, in the previous steps, we have added 2 lower digits and I've got the result in AL. If I have a carry, that will be stored in AH. Now what I'll do is, I will add AL and BH. That is, I'll add this carry with A and the result with C and then I'll get the final digits here. So I'll add the carry with the higher digit of first number and the same result with higher digit of second number. Now I have the final result. Now I'll do an ASCII adjust to adjust for the carry. Then I'll add 3030H to AX register again to convert the carry and the final result into an understandable format. Now the result in AL will be stored to BH because that is the destination of the highest digit. Then I'll copy the value of AH to CL because AH will be used in the DOS interrupt function calls in the following steps. Now I'll print the third message, which is for the sum is LEADX message 3 move AH, 09H INT 21H. Now first I'll be displaying the carry, then the next digit and then the least significant digit. So the carry is in CL. I'll display it as move DL, CL. So the interrupt 02H function code will be used for outputting and that value should be copied to DL. Its ASCII code should be copied there so that it gets displayed. So move DL, CL, move AH 02H int 21H. After that, I'll print the higher digit which is stored in BH, move DL, BH, move AH, 02H, INT 21H. Next, I'll print the least significant digit which is present in BL, that is given by move DL, BL, move AH 0 to H, INT 21H. After the execution, I'm looking for a termination from the DOS prompt if I'm using DOSBox. So I'll call the function code 4ch, which is exit, and the return code will be stored in AL to check the status of termination. So I'll copy 4ch to AH, move AH, 4ch int 21H. Since the code segment has ended, I'll mark it using the statement code ends. And since my label is also ending, I'll indicate it with the statement end start. Now I'll be showing a demo on how this program will be executed in DOSBox. DOSBox is a free and open source emulator of an Intel x86 PC. After installing DOSBox, you should also include the 8086 assembler and related files and store it in a folder. I have done it here in C drive inside a folder 8086. So I'll double click on DOSBox. Now, first I'll have to mount the 8086 assembler and related files to a local drive C. So the command for that is mount C colon space C colon slash 8086 slash 8086. My 8086 assembler files are in the location C slash 8086 slash 8086. After its successful execution, you'll find a message drive C is mounted as local directory C colon slash 8086 slash 8086. Now I need to change the control to C drive, so I'll do it by C colon. Now the control has changed from Z drive to C drive. I have saved this addition program in a file named 2.asm. In order to open it, I'll give the command edit 2.asm. Now this is the file of the program. You can see it scroll down. Now I can exit using the file menu, file, exit. So after writing an assembly program, the first step to do is assemble it. So the command will be MASM space 2.asm because I'm assembling the assembly file. Here you can see that they have asked for object file name 2.obj. So that will be the default file. If you're interested in changing the name, you can give the new name after colon. If not interested, you can click enter and skip these steps. After assembling, the next stage is to link the object files. So the format is link 2.obj. Here also they'll ask for an alternate name for the exe files. So since I'm going with the default, I have skipped it using the enter. One thing to be noted is you've seen after the assembling phase, you can see that if it's successful, we have 3 files generated. One is the obj file, next is the source listing, and the last one is for cross-referencing, which is mainly used for debugging. Similarly, when you link it, you can see that the files generated are an exe file and a map file along with the library file. I can debug the program using the command debug 2.exe. which comes with a number of command characters. I'll be using the character T, where T stands for trace. It will trace through the entire program using single step execution. So you can track the value of each register whenever a particular statement in the program is executed, as you can see in the screen. Again, I give the character T. I'll go to the next step and so on. In order to quit from this step, I'll give the letter Q. Now to execute the program, format is 2.exe. I will read the first number. I'm giving it as 74. Second number as 92. And the sum is 166. That's all. Thank you for watching.